going to present our work, Flora, low-rank adapters are secretly gradient compressors. This work has been accepted at ICML 2024 this year, and the authors are me, which is a PhD student at the University of Alberta, Yanshui Cao, a researcher at Borealis AI, and Lily Mo, my supervisor at the University of Alberta. So this is a work done by University of Alberta, Amy, Borealis AI together. In recent years, people find that scaling up neural networks is often considered an effective way to boost the performance of model. If you look at the trend of the parameter count for transformer models since it came out from 2017, you'll find that it grows more than quadratically, probably exponentially at a very fast rate. But if you look at the memory available on device, you will find that the curve is kind of flat, either for GPU or TPU. The maximum growth is only 150%. So it's compared to the parameter count, this is not enough. This poses the question of how can we utilize the limited memory available on device. So to reduce the memory usage for model training, we have to understand the components in the memory. Here's an example of training GPT-2 model with 1.5 billion parameters. So the model itself will take around 3 GB because we store it in 2-byte floating point. And the activation will probably take 4 GB, assuming the batch size equals 32 and the length of sentence is 1024. And the optimizer, Adam, will probably take 9 GB. The reason is it has the momentum, which can be stored in 2-byte floating numbers. That will take 3 GB. And there's also second moment, which is 6 GB because it usually requires to be stored in 4-byte floating point. So with this example, you see that more than 50% of memory is used by the Atom optimizer. To reduce the memory usage of optimizer, people came up with an idea called low-rank adaptation, which means we apply a matrix A and B with fewer parameters compared with original pre-training weight W. And during fine-tuning phase, we only train the matrix A and B instead of the original W. This will have fewer parameters trained during fine-tuning, but the overall change of W can only be low rank because B multiplied by A is a low rank matrix. So in our approach, we observe that the gradient of the matrix A and B is the projection of the original gradient of W times by the other part. So the gradient of A is the gradient of W multiplied by B transpose. The gradient of B is the matrix A transpose multiplied by the gradient. So if you look at this form, you will find that the change of A is less dominant than the change of B, given that the norm of B is generally smaller than A above, because B is initialized as 0 usually, and A is initialized as a random matrix. So in our paper, we have a following theorem, which basically states that the change of A tends to have a smaller effect on the overall matrix, especially when the learning rate is small. By this observation, we can approximate LoRA by freezing A. This turns the original LoRA into a random projection So if we look at the change of W, it will be the negative learning rate times A transpose, which is random projection matrix, and the original gradient. We can view this approximation in two steps. The first step is compression. We first project the gradient into a low-rank space by left multiply matrix A. This is justified by Johnson Lindstrauss lemma. We can also decompress it after compression by multiply A again. This is justified by showing A transpose is roughly the identity matrix with high probability. This figure shows the procedure of our method Flora. So we first down project the gradient with matrix A and only store it in the compressed space. And when we want to use a gradient, we decompress it with the matrix A again. This can be applied into gradient accumulation and also momentum. And most importantly, the low rank constraint in LoRA can be alleviated by simply resampling the projection matrix A. In this experiment, we demonstrate the effectiveness of Flora using the GPT-2 models. As you can see, the blue scores of Flora is higher than LoRA, while using less memory than both LoRA and the naive training. Our paper is available at this link, and we also open source our code on GitHub. You can easily use our library in your code by running this command. Thank you for your attention.